Okay, welcome to the video. I'm going to try to keep this as short as possible. This is my first video, so please excuse me if it's a little disorganized or if something isn't as fluid as it should be, but I'll try my best not to sound monotone and to explain things as simply and as quickly as possible. So let's get started. Today I'll be covering electrophilic addition reactions. So first of all, we need to know what an electrophile is. So notice the word electro here associated with like electrons, which are negative. So an electrophile is a Lewis acid, and a Lewis acid in turn is an electron pair acceptor. So an electrophile wants electrons or accepts electrons. Now why is so that's this point right here. It's attracted to negative charges / lone pairs, and why that is because electrophiles have a positive charge and or a vacant orbital that can accommodate or accept electrons from a Lewis base, or also known as a nucleophile. A Lewis base, just to clarify, is an electron pair donor. So, what does this mean? To recap, an electrophile usually has the space, so a vacant orbital that can allow for lone pairs or just electrons in general. And this is just basic concepts in chemistry. If you have well, first of all, opposite charges attract, positive and negative attract. And then second of all, if you have a lot of electrons in one area and they have the option to go to another area, they're going to go to that other area. They're going to try to get as far away as possible. This is why nucleus and Lewis bases, which have a lone pair, if given the opportunity to enter a vacant orbital, they will go and enter the vacant orbital. So that's our relationship between electrophiles and nucleophiles. They're attracted to each other. And now let's get started. So what we have right here is an alkene. Alkene, the ene means double bond. One of them is a pi bond, the other one's a sigma bond. So a pi bond's gonna be like in these p orbitals, so like between these p orbitals. And remember, orbitals are spaces, they're meant to represent electron densities. That means in this, they're gonna be a pair of electrons that go between this area right here, forming a pi bond. I don't know if that made any sense, but basically what I'm trying to say is alkenes, double bonds, there's two pairs of electrons, one in these electron clouds above and below, which is the pi orbital, and one in the sigma bond, which is between these carbons. So four electrons, two pairs of electrons. This molecule in particular is called ethene because you have two carbons. It's a 2-carbon molecule. Alright, so now let's take any acid I'm just gonna use this one because bromine's pretty awesome. Now, in chemistry, just before I start showing the mechanism, we use double-edged arrows to show that two electrons are moving, and we use single-edged arrows to show the movement of one electron. Let's just move that out of the way. Okay, it can stay there. Alright, so now what happens? You have this double bond, and we're just going to move one of those electron pairs, and we're going to give it to this hydrogen. Or not give it, but use it to attract that hydrogen over. And then because of that, hydrogen can only accept 2 electrons in their vacant orbital. By accepting these electrons, it breaks this bond, and so the electrons from that bond go to bromine. What this produces, I should draw this because these reactions, as you can imagine, is probably not the most stable, and therefore it's reversible. So now we're just gonna pick a side, and this carbon's our lucky carbon, just because it really doesn't matter, since this molecule is symmetrical and it doesn't matter which carbon gets it. But for this example, we're going to say this carbon is a lucky carbon that gets the hydrogen. And now, since it already had 2 hydrogens and it gets a 3rd hydrogen along with this bond right here, that means this carbon has, oh, first of all, I think I should draw it in so it makes more sense. Alright, so this carbon right here has 1, 2, 3, 4 electron domains, which is why it's tetrahedral. The geometry is tetrahedral, and that's why I drew it like that. The other carbon only has 1, 2, 3 electron domains. However, due to the fact that originally it had that p orbital to accommodate the pi bond, it still has that p orbital to accommodate that pi bond. So let's just write that in. This is a p orbital. These are sp2 hybridized orbitals that you may or may not understand yet right now, but if you do want me to make videos about hybridization, please let me know. I'll expand on that. Going back to our molecule over here, so this hydrogen right here is this guy right here. So it has come and attached to this carbon. Now we still have this guy, our bromine. What happened with the bromine? Let's find out. So the bromine had these 6 electrons already, but then it accepted another pair of electrons from the bond to become the bromide ion. I really should review my naming. So yeah, we have a negative charge over here. If you guys remember, that means it's Lewis base. And then over here, because that carbon only has access to 3 pairs of electrons and not the 4th pair, meaning its octet is not complete, that means this has a positive charge. Now this positive charge and this negative charge are gonna attract. So what happens is one of these electron pairs, in order to stabilize this molecule, comes and binds to, or basically this bromine is so nice that it's gonna share its electron pair and give it to carbon, so carbon can be happy too. Now it's all about making things stable. This molecule, this carbon, is so unhappy that the octet is not complete. It's gonna try to complete it, which is why it's gonna attract this bromine over. And so this is a pretty stable formation, because when you have this, it either goes back to this or it's gonna go forward into. So let's we're just gonna copy that over. This carbon is happy because it has access to 4 sets of electrons, 4 pairs. But on this other side, this carbon will accept that bromine as well as the 2 hydrogens that it already had to form this molecule. Now, again, just to go over and clarify, we have this molecule. It's not the most stable because we have an atom that does not have a complete octet, and in chemistry, completing the octet's very important. Therefore, it's going to do something to try to complete that octet. It has this right here, this p orbital that completely vacant, doesn't have any electrons. And so this bromine, which is like surrounded by all these electrons, this bromine is going to come and give some electrons into this p orbital. Now it's beneficial for both because carbon gets to complete its octet and bromine gets to spread out its electrons a bit more. And although I'm sure bromine, being the electronegative element that it is, would love to keep their electrons, overall this is more favorable than this molecule because all the octets are complete, everyone's happy, there aren't any partial charges. And so this, what we just witnessed, the addition of both this hydrogen to this carbon and this bromine to this carbon, this is called an electrophilic addition reaction because we had ethene, or a carbon-carbon double bond, and we added these other elements to them. So this is a general form of addition reactions. What our example was back here, this example, is called an electrophilic addition reaction because the electrophile started the reaction. So what this means is, what's our electrophile in this? It's this guy right here. Why is this the electrophile? Because later on it gets this charge and it like attracts this bromine. So why this this electrophile started the reaction. It provided the electrons that made this hydrogen and bromine split into two, and therefore adding hydrogen to one carbon and bromine to the other. I'm not sure if that made the most sense, if I worded things correctly. Again, this electrophile used one of these bonds, took those electron pairs to start this other reaction, giving it to hydrogen, which breaks it and gives it to bromine, which resulted in our final molecule of adding hydrogen and bromine to our ethene. And ta-da, you have the electrophilic addition reaction.